Hello, welcome to Electric Circuits Part Number 9, Introduction to Capacitors and Inductors. Now, capacitors and inductors both are storage devices. Not like a battery, they're not for a long term, but for half the time in a cycle, they are receiving power from the power source, and the other half they're receiving or returning that energy back into the circuit. Both of them do oppose the flow of current, so we call that reactance. We don't want to call it resistance because it's different, because neither one of these in our conversion convert our electric energy into heat energy like a resistor. They simply store it and return it. So we, instead of calling it resistance, we call it reactance. And as the reactance causes a phase shift. Now, what a phase shift is if you're in a purely resistive circuit, your voltage and your current will be crossing the zero reference line on an oscilloscope pattern at exactly the same place, going in the same direction. Now, in a purely capacitive or a purely inductive circuit, the voltage and the current will be exactly 90 degrees out of phase with each other. And when we mix in resistors and capacitors, or resistors and inductors, the voltage and the current will be up to 90 degrees out of phase. Now, both the capacitors and the inductors, they charge and discharge with 5 time constants. It happens really fast, and each time constant, it either charges or discharges at a rate of 63.5% of the remaining energy in the circuit, whether it's the voltage or the current that they're using. I'm going to give you a memory aid of Eli the Iceman. And like most memory aids, a little rhyme or something to help you remember. We can look at a scope pattern. If we know which one of our channels is hooked up to the voltage and which one's hooked up to the current, we can tell whether it's an inductive or a capacitive circuit, or a more inductive or more capacitive circuit, simply by looking at the scope trace. And we'll use Eli and Ice of Eli the Iceman. We'll use Eli first. The E is the symbol for electromotive force, or our voltage. L is the symbol that we use for an inductor or inductance. And I is the symbol that we use for intensity of the flow of current, or our amperage. Now, if we had our voltage and current, our channel 1 hooked up to voltage, let's say, and channel 2 on an oscilloscope hooked up to the current, we could look at that scope pattern and its phase shift and be able to tell whether it's a inductive circuit or a capacitive circuit. In this case, reading it forwards, if we was going left to right on the oscilloscope, in an inductive circuit, voltage will lead the current by up to 90 degrees. Now, if it's purely inductive, it will be 90 degrees. If we have resistors mixed in there, it'll be up to 90. Reading it backwards, right to left, as you're looking on the oscilloscope pattern, in an inductive circuit, the current would lag the voltage by up to 90 degrees. Now we'll go on to Ice. Ice is what we'll use for the capacitor. So E is still electromotive force or voltage. I is still the intensity of flow of current, or amperage. The C is our symbol that we use for a capacitor or capacitance. And we could also have that same scope pattern hooked up, and we could read it. And going forwards from left to right on the screen, in a capacitive circuit, current leads the voltage by up to 90 degrees. Again, in a purely capacitive, it would be 90 degrees. And backwards from right to left, in a capacitive circuit, voltage lags current by 90 degrees. Now, a little bit more on the definition. An inductor is an electrical component that possesses inductance. By definition, an inductor is a coil of wire, and so they're also known as coils, chokes, reactors, depending on their application. Now, because it's a coil of wire or a wire, all circuits have some inductance, even on DC. All circuits have some inductance. So current creates magnetism. Magnetism creates current. So when we have current flowing through a conductor, it creates a magnetic field on the outside of the insulator, the flux lines, if you will. That is the reason we can use clamp-on meters, is they read that magnetic field. And that's also how an inductor stores its energy as a magnetic field. And whenever you collapse that magnetic field back into the conductor, it induces the voltage. Now, an inductor opposes any sudden change in current. So it works off of trying to keep the current as constant as it can. Of course, those 5 time constants we was talking about, they happen really quick. Now, you do have to watch out for an inductive kick. If you had a large wire a mile or so long and you remove the power on it, somebody's at the other end goes to grab it, it would induce that voltage back and put them on the ground. And we call that inductive kick. Now, on a capacitor, it stores its energy. It is a component. It possesses capacitance, and it stores its energy as an electrostatic charge. 2 of the most common uses that we have for a capacitor is power factor correction and start windings or run windings of many single-phase AC motors. Single-phase here in the continental United States would be 120 volts nominal and 240 volts nominal. Now, because they work off of magnetic inductance to get these motors to start and run, it's hard to get them to start because their poles, depending on where they are in rotation when they shut down, we might not have a very good magnetic pull to get them turning. So we'll use those capacitors to give us that 90 degrees phase shift to help get it started in its rotation and everything. Sometimes we use it for to keep them running. Now, if we have start windings on a motor, remember we have to have some kind of a switch to remove those start windings. Otherwise, they would burn up real quick. Now, a capacitor will oppose any sudden change in voltage. Thank you for joining us on Part 9 of Electrical Circuits.